All right, welcome back. In this video, we are going to address why the signed area between the graph of a function and the horizontal axis is meaningful. So particularly why signed area is meaningful, why this would even be something worth looking at. So set aside what was said in a previous video about signed area being associated to an antiderivative. Let's just focus on the idea that signed area is meaningful. So here's a classic question. If velocity is 40 miles per hour and time is 3 hours, what is the total distance traveled? Well, this is not that sophisticated or complicated to imagine, but going 40 miles per hour for 3 hours, 40 miles each hour, let's see, that's 120 miles in total, right? So we could just, set this one aside by saying 120 miles and leave it at that, put a check on it, and that's that. But, I mean, hey, there's more to the story than this if we look at it from a particular point of view. And so the point of view that I'd like to encourage you to think about here is a graphical one. So a lot of times, mathematically, once we can have a geometric interpretation of something, that can offer us a lot of insight into that something. And so here is an example. We want to look at v of t with respect to time here. Time is going to be measured in hours. So for this picture, we're looking between, I suppose, 0 and 3 for time. And what is velocity? Well, velocity is just 40 miles per hour all the way across. So here is that up at 40 miles per hour, and here going from 0 to 3 hours. So now, what I'd like you to do is think, well, how could this 120 miles of distance traveled ultimately relate to this picture? And well, if you think about it, the height of, well, we see this rectangle here that is the signed area between this function's graph and the horizontal axis, and the height of that rectangle is 40 miles per hour. The width of that rectangle is 3 hours. And so if we just compute the area here, the area is going to be the height, 40 miles per hour, times the width of 3 hours, which the hours are going to cancel here, miles per hour times hour, and we're going to get ultimately 120 miles. And note, this is the exact same measure that we got previously whenever we just trusted our intuition and computed without the picture. Now, you could say, but yo prof, why do I care about this picture whenever I can resolve the question without the picture? Well, the purpose is to realize that within this picture, we now have a new way to interpret distance traveled in relation to velocity, which is to say that distance traveled in some way must relate to the velocity, and the time in some way must relate to the graph of that velocity over the time interval of interest. Because as we see in this example, where we have a constant velocity of 40 miles per hour over our 3 hours, the signed area between that function's graph and the horizontal axis turns out to be the exact distance that was traveled by the object. Now, I just want to make a note here about the word signed on our area. The notion of signed area means when our function is above the horizontal axis, the area will be computed positively. When the function is below the horizontal axis, the area will be computed negatively. Now, this will come into play here with example 2. So in this case, we have a velocity function which during some of the time interval is positive, and during other portions of the time interval is negative. So when we think about positive velocity and negative velocity, we could think moving in one direction and then moving in the other, right? So normally whenever we talk about velocity being either plus or minus, we're sort of thinking in like almost a linear path. You could think of maybe this is the velocity of you traveling to class, sitting through class when you have no velocity, you're just sitting in your seat, to ultimately then heading back home, right? So going from home to class, we denoted that with positive velocity, and then going from class back to home, we denoted that as negative velocity. So here would be an example graph of your velocity maybe this morning, coming to class, sitting through class, and then heading back to home, wherever that may be. And now, thinking about the picture that we had previously when we looked at the velocity relating to the distance traveled. That could also then relate in this picture where we don't just have a constant velocity, right? As you were walking your way to class, you were sort of speeding up to your normal walking rate, and then you were sort of slowing down as you got to your seat, and then you were sort of speeding back up as you were walking your way home and getting to your sort of like normal walking pace, and then slowing back down whenever you arrived home to, sit down at your desk and do whatever else you wanted to do once you got home. But now, thinking about the area here, right? There's an area region above the horizontal axis, which should relate to distance traveled. If you think about it, right? What if you even just took this area region and tried to approximate how much area was contained within it using rectangles, right? These rectangles would have to relate to the distance traveled, because when you think about each of these rectangles, the height of each of these rectangles is some velocity, say in miles per hour. The width of each of these rectangles is some amount of time, say in terms of hours. So the area of each of these rectangles is just some number of miles per hour times some number of hours, which ultimately comes out to be some number of miles as a result. And so I'm not inserting exactly what the measures are here. Let me fit this on the page here. So some number of miles per hour times some number of hours will ultimately give you some number of miles, just focusing on the units of interest here. But yeah, look, the long story short is the area that is under a velocity function is giving you insight to the distance that has been traveled by the object that is being tracked by that velocity function. And so this area above the horizontal axis is corresponding to a distance traveled from home to class, and then you were sitting in class when your velocity was 0, meaning that the miles that were being traveled during that time was also 0, and then as time passed, you ultimately headed your way back home. Note, each of the rectangles that might be used to approximate this area region are now beneath the horizontal axis, and so in terms of signed area, each of these rectangles is going to have a mile per hour measure that's going to be negative, because the velocity here is negative during this time when we were walking from school back to home. And now that means that this distance traveled is going to be computed negatively. But now if you think about this, between, let's say, time A here, when this picture begins, and time B here, where this picture ends, well, there was some amount of positive distance that was traveled whenever you were going from home to class. There was some amount of negative distance that was traveled when you were going from class to home. And when you put this all together, the total signed area on the interval from A to B is going to be just 0, right? Because there's some amount of positive signed area above the horizontal axis, some amount of negative signed area beneath the horizontal axis, but that positive signed area and negative signed area cancel each other out, which actually makes sense, right? Because you started from home. You ended at home. Yes, you traveled to class, then you traveled back from class in between, but between your starting and ending point, the total net distance traveled is 0. And so this signed area must, in some sense, relate to like a net distance traveled. And indeed, it does. Oftentimes in physics, we call sort of the net distance traveled the displacement. And your displacement would be 0 miles in the event that you started from home and you ended from home, traveling to and from class in between. And so, look, the purpose of this discussion is not to go into too much physical detail about the intricacies of the signed area in the case of a velocity function, but rather really just to emphasize the fact that the area between a function's graph and the horizontal axis can be meaningful. Take a velocity function, the area between the velocity function and the horizontal axis definitely relates to the distance traveled. You've got a constant velocity, that's going to sketch out a rectangle. You've got a non-constant velocity, so be it, that's going to sketch out area regions, which you could approximate by rectangles, but nonetheless, area regions that are also associated to distance. And if you think about the physical meaning of going to class and then coming back home, this positive distance traveling to class and this negative distance traveling back from class, the fact that those two area regions would cancel makes a whole hell of a lot of sense. And so ultimately, signed area has meaning within context, if nothing else, through a velocity function and the area underneath it. But in general, signed area can be meaningful. So studying and understanding signed area is something that would certainly be worthwhile so that we could wrap our minds around the meaning that would be associated with this idea.